So let's go ahead and take a step-by-step look at each of these problems. The first one I have already written out. I'm just going to go over the step-by-step process here. Now numbers 11 and 22 were very similar with finding the derivatives. So let's take a look at number 11. Now also with these, it's very good to note the domain. So for number 11, because I have a square root, I know what's inside could equal 0 or it could be larger than 0. So since I'm subtracting an x squared from 8, I know x squared cannot be greater than 8. So as long as I'm at negative radical 8, that would give me a 0 here, and a positive radical 8 would give me a 0 if I square that and subtract from 8. And anything in between would be less than 8 when I squared it. But anything over positive radical 8 or below negative radical 8, that would give me a value larger than 8. So I have to stay in between the radical 8s here. And just to note that radical 8 simplifies to 2 radical 2. So this is now a closed interval, so we are guaranteeing absolute max. It's a continuous function on a closed interval, so the extreme value theorem applies here. So let's first take a look at the first derivative. So I have to use the product rule. So I'm going to underline the parts here. So u is just x. Now v prime is right here. We have 1/2 times the quantity 8 minus x squared to the negative 1/2 times the derivative of the inside stuff, which is negative 2x. So there's my u v prime. So this is v. Then I have plus v, which is the square root of 8 minus x squared. U prime is just 1. So now I want to carefully clean this up. So in the first part here, this 2 with this 2 divides out, so I'm left with an x times a negative x, so I get a negative x squared up top over the square root of 8 minus x squared, plus this square root, which I'm going to put over 1. And now, in order to ask myself these two questions off to the right, I want to get this as one fraction. So I'm going to multiply the second fraction, top and bottom, by radical 8 minus x squared. It's going to allow me to write this as one big fraction. So now up top, I have negative x squared. When I multiply these two quantities together, I just get plus 8 minus x squared, so I don't really need parentheses, all over my common denominator of radical 8 minus x squared. Just combining like terms, and sometimes it helps to, if possible, write our numerator in factor form, because now when I ask myself these two questions, where is our first derivative equal to 0? That's when our numerator is equal to 0. We could solve by factoring, or we could just use inverse operations. So I'll just add 2x squared to both sides, divide by 2, carefully take the square root, so I get plus or minus 2. Y prime is undefined when my denominator is equal to 0, or just the stuff underneath the radical is equal to 0. Well, guess what? This gives me my endpoints here. And I know when x is plus or minus radical 8, I'm going to get a 0. So we could also write that as plus or minus radical 2 radical 2. All right, so now we want to make our first derivative number line. Now at the negative radical 8 or negative 2 radical 2 to 2 radical 2, I'm going to put brackets here because I'm not going to test outside of those brackets. I could look at what I have underlined here or here to do the plus or minus test. So let's say I chose a negative 2.1. If you wanted to, you could calculate negative 2 radical 2. But it's definitely, in this case, negative 2 radical 2 is less than a negative 2.1. So imagine substituting in a negative 2.1 here. If I were to square that, that's going to be larger than 4. So I get 2 times a negative number divided by a positive number, so that's negative. Imagine I test 0 in the middle. That's going to give me a positive times a positive over a positive, so everything in between the negative 2 and 2 are positive. And then I would also get a negative over here, because just imagine substituting in a positive 2.1. I'd get 4 minus something that's larger, so that's negative. So this tells me y is decreasing, then increasing, then decreasing. Now again, I'm guaranteed an absolute max and min, so the absolute min happens when x is negative 2. The absolute max happens at x is positive 2. Now we have to carefully find our second derivative. I'm going to use this version. We're going to use the quotient rule. So again, my low, d high. So low is my denominator here. My derivative of my numerator is just a negative 4x. Minus my high. Now d low becomes, here's that 1/2, times the quantity 8 minus x squared to the negative 1/2 times the derivative of the inside stuff. Over low, low, so the square root of this quantity squared. Now everything over here is going to become its own little fraction. It doesn't drop to the overall denominator, but we create its own little fraction. I'm just going to rewrite the first part. Just look at what's inside here. I'm just going to rewrite this first part as negative 4x times the square root of 8 minus x squared. Now where did this plus sign come from? I have this minus sign here, and it gets multiplied by this negative 2x, so that's where we're getting the plus sign from. This 2 and this 2 cancel out, so up top I'm left with an x times this quantity 8 minus 2x squared. This quantity right here becomes the square root that's right here. Now to get rid of that, I'm going to multiply top and bottom by the square root of 8 minus x squared. Once we do that, this is what becomes of our next step. Negative 4x, when I multiply this radical by this radical here, I just get 8 minus x squared, plus, then I'm just left with x times this quantity, over, and I'll just leave it as this quantity times the square root of that. And then I'll just continue to simplify. So distributing here, negative 32x plus 4x cubed, over here plus 8x minus 2x cubed. That gives me 2x cubed minus 24x in my numerator, which we could also factor. And I just leave my denominator the same. So now I'm going to ask myself the two questions. Where is our second derivative equal to 0? Where our numerator is equal to 0. Again, I want to factor this. So when I do, I get x is equal to 0, or x squared minus 12 is equal to 0. When I solve this, I get plus or minus the square root of 12, which is plus or minus 2 radical 3. Well, 2 radical 3 positive is greater than 2 radical 2. Negative 2 radical 3 is less than negative 2 radical 2, so that's outside the domain, so we don't even worry about that. Our second derivative is undefined also at the ends for plus or minus 2 radical 2. So I only have one critical number here. I'm going to make my second derivative number line. Again, put the brackets. I'm only testing on either side of 0. So if I substituted a negative 1 back into, we'll say this version of it, 2 times negative 1 is negative. Negative 1 squared minus 12 is still negative. So I get a negative divided by my denominator is always positive. So a negative times a negative is a positive over a positive gives me positive. When x is 1, I'll get a positive times a negative over a positive, so that's negative. So here's our concavity, and we have a point of inflection at x equals 0. Now we have to find our special points. So again, our function, we're going to do all this by hand. So f of negative 2, you could see the work here becomes negative 4. F of 2 becomes positive 4. Those were our extrema. F of 0 is 0. And then at the ends, plus or minus radical 8 or plus or minus 2 radical 2, that gives us 0. So let's go through our summary. Our function is increasing from negative 2 to 2. Our function is decreasing, and because these are the endpoints, I put the brackets here. Now on my solutions with work, just the PDF, I forgot to put my negative here, but it goes from negative 2 radical 2 to negative 2, and then from 2 to 2 radical 2. Concave up, again at the ends, I should have brackets. So even right here, should have a bracket. Our absolute max is y equals 4 when x equals 2. Our absolute min is y equals negative 4 when x equals negative 2. We have a point of inflection at 0, 0. So let's plot these points. Here's the point 0, 0. I just counted by 1s here up to 4s all around. Here I have 2, 4. That's where my absolute max is. Negative 2, negative 4. That's where my absolute min is. And then roughly 2 radical 2 is pretty close to 3, so we'll put a point here and then over here. And I know that those are at 0. All right, so first we know we're decreasing and we're concave up. So it's going to look like this. Then we're increasing from negative 2 to 2, but from negative 2 to 0, we are still concave up. We change concavity at the origin, so now we're increasing, still concave down. And we're still concave down, but now we're decreasing. So this is what a sketch of our graph should look like. All right, 15, a little bit easier, not nearly as long as number 11. All right, so here's our function. Our domain, we are good for all real numbers x. So let's carefully go through and find our first derivative. So this will become 2 times 1/5, so we get 2/5 x. 1/5 minus 1, 1/5 minus 5/5 will give us negative 4/5. Derivative of a constant is 0. So let's rewrite this as a fraction to help us answer our next two questions. So this becomes 2 over 5 times the 5th root of x to the 4th. So where is y prime equal to 0? When our fraction is equal to 0 when our numerator is equal to 0. Our numerator is 2. 2 can never equal 0, so never. Not our second derivative. Where is our first derivative? Undefined. And that's when x is going to equal 0. So we make our first derivative number line. We only have one critical number here. That also makes it nice. So I could test a -1. So if I raise -1 to the 4th, that's positive, and then everything's positive here. If I raise a +1 to the 4th, that's still positive. So y is increasing everywhere. So we have no extrema. No extrema here. Let's go ahead and find our second derivative. I'm going to use this version to help us out. So now I'm going to take 2/5 times negative 4/5. So that's giving me negative 8/25 times x to the negative 4/5 minus 5/5 is negative 9/5. Cleaning this up, I'll have a negative 8 over 25 times the 5th root of x to the 9th. Now, technically, we could leave it like that, but I am going to simplify it. It'll just make it a little bit easier when we go to do our number line test. So we're going to have negative 8 over 25. Now, think of factoring this into x to the 5th times x to the 4th. So an x will come out, and then we'll have the 5th root of x to the 4th. So we'll go ahead and make our second determine where this is equal to 0 and where this is undefined. Again, our numerator is a constant, so that will be never. And then this, again, will be undefined when x is 0. So we'll make our second derivative number line. Put 0 here. Again, if I test a -1, this radical will be positive, but then I'll have a negative here, and a negative divided by a negative will give me a positive. And then when x is 1, everything in the denominator will be positive, so I'll get a negative 8 divided by a positive, so that's negative. So then y is first concave up, concave down after 0. Therefore, we do have a point of inflection at x equals 0. All right, so really 0 is our only value we need to deal with. So when x is 0, y is equal to 2 times 0 to the 1/5, which is 0 plus 3. So we have an ordered pair here of 0, 3. All right, so let's get our summary written out. For part A, let's show where this is increasing. Now, because we do have a point of inflection at 0, I'm still going to write the increasing intervals separate. So we're going to say from -infinity to 0 and 0 to infinity. Decreasing, there are no intervals where our function is decreasing. Concave up from -infinity to 0. Concave down, 0 to infinity. We have no extrema. And our point of inflection is at 0, 3. All right, so let's make a sketch of this. All right, so again, I know I have my only special point here. It's at 0, 3. So I know before that I am increasing and we are concave up. Now, again, based off of the nature of this graph, we have 2 to some power. So it's an exponential, or 2 times x to 1/5 here. So eventually this could cross the x-axis. We don't know when. And again, this is just a possible sketch. So we're looking at increasing and concave up. So we could do something like this. Now we know our first derivative is undefined, so we should expect a vertical tangent, so we can go up a little more. And then we're still increasing, but we're concave down. So it looks something like this. Okay, let's take a look at number 19. We have a piecewise function. Now, as far as piecewise functions go, this is pretty basic. We really don't need to analyze this, but it's still nice to tie this in even when our functions are a little more basic. Definitely makes the derivative, finding the derivatives, a lot easier. One thing we need to point out here is kind of like the domain. If you substituted in a 1 here, you would get a 2. And then if you substituted in a 1 here, you would get a 1. So the left-hand limit coming from the left of 1 and then versus coming from the right of 1 does not exist or does not equal the right-hand limit. Therefore, y is not continuous at x equals 1. So that means the value x equals 1 is going to be a nice critical number for us to test. So let's find our first derivative. And we just simply take the derivatives of each piece. So we'll have a 2 and we'll have a negative 2x. When x is less than 1, when x is greater than or equal to 1. So we'll ask ourselves, where is y prime equal to 0? Well, never, because in the second part, it could equal 0 when x is 0, but then that would put us up here. So it will never equal 0. Is y prime ever undefined? No. But we still need to see where our function is increasing or decreasing, so we're still going to make a first derivative number line. Even though I have no critical numbers, I am going to use this number 1 because it sort of separates the graph. So I need to see how the graph is behaving on each side. All right, so when x is less than 1, I have a constant here of 2, so that's always positive. When x is greater than 1, negative 2 times any number greater than 1, that's always going to be negative. So my function y is increasing, then decreasing. Now let's find our second derivative. And again, I just take the derivative of each piece. Derivative of a constant is 0. Derivative of negative 2x is just negative 2. Ask ourselves the two questions. Where is our second derivative equal to 0? When x, it's always 0 when x is less than 1. Where is it undefined? Never. So we'll make ourselves the second derivative number line. We'll still put 1 here. Now, we're not going to get a plus or minus. It's always 0 here. But over here, when x is greater than 1, our second derivative is negative. So there's no concavity for less than 1. And if you notice the original function, y equals 2x, it's linear, so there's no curve to it whatsoever. But then we're concave down afterwards. So what this still means is no point of inflection. Also up here for our first derivative, since our function is not continuous at x equals 1, we say f of 1 does not exist. So there's no extrema. But knowing where our function is increasing and decreasing and concave up or concave down still matters. All right, so we can go ahead and write out our summary. All right, so for increasing, we know our function is increasing from negative infinity to 1, decreasing from 1 to infinity, concave up, never, or there's no interval with that, concave down from 1 to infinity, no extrema. Again, f of 1 does not exist, and no points of inflection. But we could still graph this for sure because we know what the piecewise function is giving us here. All right, so for the first part, we're looking at something that's linear, so we could just go back to y equals 2x, but we know we're increasing and there's no concavity, so that also tells us we're linear. But if we graphed y equals 2x, we know that's going to pass through the origin, and we go up to 1, but this is for x is just less than 1. So we're going to have an open endpoint right here, and it's going to look like this. And then for y equals 2 minus x squared, we're going to have a y-intercept of 2, but it doesn't exist there because this is just for x is greater than or equal to 1. So when we're at 1, we're going to be right here. This will be a closed endpoint. So imagine like our vertex would be right here on the y-axis. We go over 1, down 1. Going back, we can go over 2, down 4. And again, we're going to be decreasing and concave down there. All right, so let's go through number 22. Very similar to number 11 as far as stating the domain and finding first and second derivatives. So here we have x squared times the square root of 9 minus x squared. So our domain, what would make this 0 is when x is -3 to +3, and we have to stay within them. Because if we were larger than +3 or less than -3, we would get a negative underneath our radical. This is also a closed interval. So the extreme value theorem applies here. We're guaranteed an absolute max and absolute min. So let's find our first derivative. uv prime becomes x squared times 1/2 times this quantity to the -1/2 times the derivative of the inside stuff plus v, and then u prime is just going to give us a 2x, so we can say 2x times the quantity 9 minus x squared. So cleaning this up, just like the last one, or number 11, we're going to get an x cubed, negative x cubed up top. The 2's are going to divide out over the square root of 9 minus x squared, and then plus 2 times this quantity. We could say over 1, so to get common denominators, let's multiply this by 9 minus x squared, radical 9 minus x squared, that is. So now we're going to get negative x cubed plus 2x times the quantity 9 minus x squared all over the square root of 9 minus x squared. Distributing and combining like terms, I'm just going to fast forward a little bit here. We're going to get an 18x minus 3x cubed all over this. And we could factor out a 3x, and then we would have 6 minus x squared over the square root, and that's going to help us a little bit. All right, so where is y prime equal to 0? When our numerator, 3x times 6 minus x squared, is equal to 0. So this is when x is equal to 0, or 6 is equal to x squared, so x equals plus or minus the square root of 6. Where is y prime undefined? When x equals plus or minus 3. So use your calculator. The square root of 6 is approximately 2.449, so that's going to help us. So when we make our first derivative number line, again, we're just going from -3 to 3. So we also have roughly a negative square root of 6. We have a 0, and we have a positive square root of 6. So again, we have brackets here and here. Now, you could use your calculator to test this. You could define your function if you choose to here. If not, you could substitute everything right back into here and determine if you get positives or negatives. But again, you could use your calculator, and in doing so, let's say you tested a negative 2.7 here and then a positive 2.7. You should be getting positives over there. That'd be different on that end if it were positive. In between negative radical 6 and 0, that should be negative. You should get a positive between 0 and radical 6 and then a negative over here. So this tells us y is increasing, then decreasing, increasing again, and then decreasing. So we have an absolute max at x equals negative radical 6 and at x equals positive radical 6. And then we have an absolute min at x equals 0. And you'll see that those two values will come out to be the same anyway, so we're going to have two values that would be considered the absolute max. All right, so let's go ahead and find our second derivative. I'm going to use this version of it very carefully. We have low. D high becomes 18 minus 9x squared minus high, which is 18x minus 3x cubed. D low becomes 1/2 times this quantity to the negative 1/2 times negative 2x all over low, so that's just going to give us 9 minus x squared. We're squaring the square root. All right, so again, like 11, cleaning this up, I'll just rewrite this out in front. It should be 18x. No, that should have been an 18. That was a derivative. All right, so we have 18 minus 9x squared times the square root. Again, over here, we're going to get a positive. The 2's cancel, so up top I have x times 18x minus 3x cubed all over the square root of 9 minus x squared. This is all over 9 minus x squared. So like in number 11, I'm going to multiply everything up here by the square root and everything down here by the square root. So in doing that, I get 18 minus 9x squared times the quantity 9 minus x squared plus x times the quantity 18x minus 3x cubed all over this. All right, so we have to carefully distribute here. And you could do this by hand. You don't necessarily need a calculator, but remember, on this one you were allowed. So we have 162 minus 18x squared minus 81x squared plus 9x to the 4th plus 18x squared minus 3x to the 4th. All right, combining our like terms, we should end up with 6x to the 4th minus 81x squared plus 162 up top. All right, so now we can ask ourselves our 2 questions. Definitely use our calculator to help us out. Going first to where it's undefined, just like in the first derivative at plus or minus 3. Here we would set our numerator equal to 0. You definitely use the solve feature on your calculator. And here we should get plus or minus 1.563. We'll make our second derivative number line. So you could pause the video if you wanted to try typing that in there. Again, we have our 3's. We have our negative 1.563, positive 1.563. So this is on the calculator. This is where you want to use the define feature. Type in this for our second derivative, and then you can test your values. Again, we need to stop. We have to stay within the 3's. So you should get a negative, positive, negative. Therefore, we are concave down, then concave up, concave down. So we have points of inflections at both of those values. All right, so again, we're going to include anything with the negative 3. So our summary here, function is increasing. We're going to say from negative 3, but we're including that to a negative radical 6, and then from 0 to radical 6. Decreasing in between, negative radical 6 to 0, and then from radical 6 to positive 3. Concave up between the 1.563's. Concave down. Again, we include the 3's. So again, you can define your original function. You could get it should give this to you as an approximate value, and this isn't going to be too hard to figure out by hand either, but when we go to sketch the graph, we want the decimal approximations. So here, for the absolute max, it's actually y equals 6 radical 3, which is roughly 10.392 when x is negative radical 6 and positive radical 6. Our absolute min is y equals 0 when x equals -3, and +3. For f of the points of inflection, you just have to evaluate the function at these two values, the -1.563 and the positive. So we get -1.563 and 6.256, and then +1.563 and then 6.256. So let's make a sketch. So because I have to go up to about a 10, a little over 10, I'm going to count by 2's on my y-axis. All right, so I know at -3 we're at 0, +3 we're at 0. Oh, I forgot that. Also, the absolute min when x is also equal to 0, so let's put that in there. I have points of inflection at a -1.5, so roughly right about here, and then on the other side as well. And then my max is at 10.392. Again, radical 6 is about 2.5. So we're going to -2.5, a little over 10, +2.5. All right, so to graph this, I know I'm first increasing and concave down. It's going to look like that. Then we're still concave down, but we're decreasing, so right about here. And then we're still decreasing, but now we're concave up. Here's our absolute min there. Increasing, concave up. Point of inflection, turn to concave down, still increasing. And then we're decreasing, concave down. All right, so hopefully this helps. Please let me know if you have any other questions.